So now we're looking at, yesterday we built like reaction series and fitness. Today we're going to look at if you put a whole bunch of things together in, a beaker, what two substances are going to react. So that's what we're going to look at today. So first of all, I'll give you a few step-by-step process to figure these out. So the first thing you should do is list all species present as reactants. Now, when you're doing this, you kind of want to break things down according to the following rules. And I'll just kind of highlight things here that I would like you, I guess, to write down if you're writing notes. So list all species present as reactants. So you need to disassociate soluble ionic compounds and acids. Now, remember, if you are disassociating soluble ionic compounds, for example, go ahead. So calcium chloride, for example. To disassociate this, it would be coming into calcium as a 2+ aqueous ion, and chlorine negative aqueous ion, right? A lot of people on the quiz were messing up and putting the subscript there, but once it disassociates in water, there's actually 2 of those chlorine negative ions. And acids, as soon as you see an acid present, you would have to include hydrogen. If you've seen a base present, and I think it's written down here, oh, maybe not. For base, you would have to include hydroxide. You do not disassociate molecular compounds. So if, like, for example, there was sugar in all of the beakers that you were adding in, you would just leave sugar as the molecule C6H12O6, because molecular compounds don't disassociate. They just get surrounded by water. We already talked about acids, and you always need to include water in your reactants, because all of these are happening in an aqueous environment. Oh, now that's in my way. Okay, next. All right, so second step is once you have listed all the reactants, then you're going to go through them and identify which ones are possible oxidizing agents and which ones are possible reducing agents. And you'll just identify which ones have each category. The thing you have to know is there are 4 compounds that we look at, or I guess ions, that can be both oxidizing and reducing agents, which are these ones: iron, chromium, tin, and water. They can act as both oxidizing agents and reducing agents. And maybe when you were looking at the questions yesterday, you ran into this. So I honestly can't find this anywhere else. So Mr. Shelley must have made it up on his notes. And his way to remember this is feel. Yeah. Apparently it works. I don't know. So iron, right? Fe. This is water. This is chromium. And this is tin. He had to make it up because I Googled it and tried to find a picture if it was used anywhere else. Apparently it's not.
What did you find when you Googled it's not?
Nothing came up actually, so just. Yeah. So then once you've identified everything as oxidizing and reducing agents, what you need to do is figure out which 2 are the strongest oxidizing agents and strongest reducing agents based off that table in the data booklet. Once you've identified which ones are the strongest, well, then those are going to be the ones that are going to be reacting. Everything else we ignore as a spectator ion. So you'd write out the half reactions for each of those, determine the net ionic reaction, and then you determine if they're going to react or not. Because even though maybe one is the strongest reducing agent and strongest oxidizing agent, it doesn't necessarily mean they're going to undergo a spontaneous reaction. Maybe you still need to add heat in order for them to have that reaction. And so I think that this is kind of just a reiteration of what we've talked about. Aqueous solutions contain water, acids contain hydrogen ions, basic contain hydroxides. Some OAs and RAs are both OAs and RAs. Feel hot, green, snow. And then, so here's the last one that we need to make sure what we're doing here. The strongest OA and the strongest RA are going to react from all species, and everything else is ignored as a spectator ion. And so some general rules to follow And I mean, you don't really have to commit these to memory because if you're going to go through this step-by-step process of memorizing them anyways, you don't really need to memorize these last two lines here. So the most reactive metal is usually the strongest that should say Ra. And the least reactive metal would be your OA. And so remember, if this is my table, this is my SRAs down here, which are generally metals, and my SOAs up here, which are metal ions and polyatomic ions. Usually, what we're going to see here is ones that are reacting with hydrogen in an acidic environment. So let's look at exactly how this works. So here's the example. Predict the most likely redox reaction when chromium is placed into aqueous zinc sulfate. Now, before we were just assuming that chromium and zinc were going to change places in a double refrigerant reaction, but once we start adding acidic and water into here, it's not always the case. So the first thing we need to do is write down every single possible reaction. So chromium is in its solid form, so chromium solid is placed into aqueous zinc sulfate. So that means that zinc sulfate is an ionic compound, so it would dissociate into its ions. So I would have a zinc 2+ aqueous ion. Sulfate is an SO4 2- aqueous ion. And because this reaction is happening in water, I always include water as part of my reactants. Okay. So once I've listed all my reactants, I need to, go look at my table, or some of these I can kind of figure out off the top of my head what they are, but I need to have my table as a reference to figure out what would be the strongest, what would be the weakest. So chromium, is that going to be an oxidizing agent or a reducing agent, without even looking on here? It's a reducing agent because it's a metal, so this is a reducing agent. Zinc is an ion, so it's probably a oxidizing agent. SO4 2-, we've never really dealt with that before. But if you combine SO4 2- with water, I think, where is it? It's right in the middle. It's right just under copper. It's an oxidizing agent. If these two are together, it's an oxidizing agent. And water is part of that feel hot, creamy, whatever. It acts as both an OA and an RA. So that's my second step, is to figure out which ones are OAs, which ones are RAs. Then, based on my table, what I'm going to do is figure out which one is the strongest reducing agent and which one is the strongest oxidizing agent. So if I go look at my reducing agents on this table, chromium is down here and water is kind of right in the middle. So chromium is my strongest reducing agent. And then I have to debate between sulfate reacting with water by itself, or zinc as the strongest oxidizing agent. And if you go on here, it is zinc.
Why do you have those two arrows connecting to OA?
Because sulfate ions are never by themselves. They will have to react with water in order to undergo a reaction. So because I figured out this is the strongest oxidizing agent and the strongest reducing agent, then I can just go write out my half reactions. So chromium is solid, and chromium is likely breaking down into its ion, which is Cr2+ aqueous. In order to write that balanced half reaction, I'd have to add 2 electrons, or I could technically just copy the exact reaction that's on my table here. Right now I'm going this way for my reducing agent. So that's chromium. Zinc is Zn2+ aqueous. In order for that to be neutral, it would have to react with 2 electrons, and it would be producing zinc solid. As a net, so these are my half reactions. As a net, I don't really have to multiply here by anything because the number of electrons are the same, which would cancel out when I'm trying to go determine my net equation. So chromium solid is reacting with zinc 2+ aqueous to produce chromium and so there is my net reaction. Yes, yeah. In your net equations, you generally don't have the inclusion of electrons. In your half reactions, you have inclusion of electrons. Okay, so let's look at another more complicated example. There's the answer. Beautiful. Okay, so I'll do one more and then you guys can do one. Predict the most likely redox reaction when potassium permanganate is slowly poured into an acidic iron 2 sulfate solution. So I have to write out everything here. So the first thing here is potassium permanganate. That is ionic, so it would break apart into its ions. So potassium, you guys are really distracting me, those two ladies there. Potassium, which is K+, and permanganate, which is an ion on my chart, which is MnO4 negative, aqueous, is slowly poured into acidic iron 2 sulfate. So acidic means I'm going to have hydrogen's ions. I have to include that as part of my possible reactants. Iron, which is Fe2+, aqueous, and sulfate, SO4, 2 negative, aqueous. And as always, we have to include water as one of our possible reactants. So once I've broken everything into the ions and wrote out all the reactants, then my next step is to figure out which of them is an oxidizing agent and which of them is a reducing agent. So I know for sure that zinc is an OA and an RA, and so is water. It's an OA and an RA. Pardon me? Sorry, did I say zinc? Sorry, yes, thank you, iron. And from last question, I know that these two can react and they are oxidizing agents. Potassium, because it's a metal ion, is an oxidizing agent. And then I need to go look at permanganate. Well, on here, permanganate reacting with hydrogen ions is almost at the very top. So I'm going to just assume that it's my strongest oxidizing agent. It's the third reaction from the top. So, because we're not dealing with lead oxide or fluoride. That's probably my SOA. So then I just need to go figure out what my SRA is. And I don't think anything else here reacts in terms of a reducing agent. So it's between water and zinc. And so if I go check my half reaction tables for my reducing, why did I put, oh yeah, zinc is a reducing agent. If I look and compare, this is my oxidizing agent, my strongest oxidizing agent, and permanganate is my strongest reducing agent. Or sorry, mix those around. Right there. Then I just have to go write the half reactions. So I don't even need to go figure out this out because I can just write the half reaction that's already on my table, right? I don't need to do what we were doing before and create the half reactions because this is already on here for me. So if I go to, this is permanganate, is reacting with 8 hydrogens and 5 electrons to produce a manganese ion and 4 waters. And iron is Fe2+, and because it's a reducing agent, Fe2+ is becoming Fe3+, aqueous, and, 1 electron. So to create my net ionic equation, I need to have the same amount of electrons being transferred from reducing agent to oxidizing agent. So what would I have to do here in order to have the same amount of electrons? Right, so I'll times this guy by 5, and so technically that would cancel out these number of electrons. So the total net would be my permanganate ion reacting with the 8 hydrogen ions from that acidic environment, as well as reacting with zinc, zinc, why do I keep saying that? Iron 2+ aqueous to produce what's left, which is the zinc 3+ aqueous ion, the manganese ion, and we also have the inclusion of water here. And that would be my net reaction. Oh, I messed up. Anybody know where I messed up? There's no 5s, right? These should technically all be 5 because I times it by 5. So 5 here and a 5 here. If you're watching the video, try the next question by yourself and do homework number 1.